Hi everyone, a very good evening to all of you. Welcome you all to the online session of Gurukul Academy. तो चलिए आज की क्लास को शुरू करते हैं. आज की क्लास में आपके साथ मैं डिस्कस करने जा रही हूँ एक बहुत बहुत इंटरेस्टिंग अ ग्राउंड ब्रेकिंग एक्सपेरिमेंट इन द न्यूक्लियर फिजिक्स. सो लेट्स गेट स्टार्टेड विद द सेशन. जल्दी से सेशन को ज्वाइन करो और फिर आपके साथ डिस्कस करते हैं न्यूक्लियर फिजिक्स का वन ऑफ द फैसिनेटिंग एंड द ग्राउंड ब्रेकिंग एक्सपेरिमेंट. What happened to the board? Let's just wait for 1 minute. Ma'am, panel, no signal. चल पड़ा. Yes. So what I was talking about we are going to discuss. Very good evening, very good evening. So today we are going to discuss about the most groundbreaking experiment which challenges the fundamental of physics community, and physics community was in really shocked after the result of the experiment, that is the Wu experiment of the cobalt 60 beta decay. So let's move towards the experiment of cobalt 60 beta decay. Okay, so today we are going to discuss about the cobalt 60 beta decay, the Wu experiment, a groundbreaking study in the nuclear physics that challenged the fundamental principle of physics. So let us write the Wu experiment. So the Wu experiment was a groundbreaking experiment which challenges the fundamental principle of nuclear physics and which shows that the parity is violated during the weak interaction. Parity So actually what is happening is that the universe should have the equivalence for the right-handed and the left-handed coordinate system, because the parity should not be getted violated during the process, but during the weak interaction, during the study of the cobalt 60 getting through the beta decay and get converted into the nickel 60, and there is emission of electron and antineutrino, what we observed that the electrons are emitted antisymmetrically. There are two scenarios in which the electrons should be emitted. So let us study that two scenarios. So in that two scenarios, what is the main aim? Let us study in detail about the experiment. So 60 cobalt should convert it into the nickel, 60, and there should be the emission of electron and an anti-neutrino. But we have seen that there are only right-handed anti-neutrino exist in the universe. Right-handed antineutrino exists only. Okay, so there and neutrinos are always left-handed. And neutrinos are always left-handed. So what is happening is that cobalt 60 when get converted into nickel plus electron, there are two scenarios. Scenario number one is that the cobalt 60 in this direction, and the electron is emitting in the reverse direction. The momentum vector of electron is in the reverse direction as that of the cobalt 60. The electron is in the opposite direction as that of its spin vector. Okay, as that of its spin vector, and the antineutrino has the spin vector in the same direction as that of the momentum vector, that is right-handed antineutrino. This is the one scenario. And now let us study about the scenario number 2. The scenario number 2 is that the cobalt 60 in this direction, but the electrons are emitted in the same direction as that of cobalt 60, but there are left-handed antineutrino emitted. Now, these can be two scenarios that are possible in the case of beta decay. The cobalt 60 is the nuclear spin and the electron spin are opposite to each other, and there is an emission of a right-handed antineutrino, and the scenario number 2 is that the electrons are in the same direction as that of cobalt 60, and there can be emission of left-handed antineutrino. But what happened is that both the scenarios are allowed from the point of view of the conservation of linear momentum and energy. There is no violation in the both scenarios, but we find that the electrons are emitted antisymmetrically. Most probably the electrons are always pointed in the opposite direction as that of the cobalt 60. There is a non-equivalence between the left-handed and the right-handed antineutrino. The universe preferably emitted the electron spin in the opposite direction of cobalt 60, and there is an emission of right-handed antineutrino. In the universe, we have not found any left-handed antineutrino till now. So this results in the parity violation during the beta decay. And that's why we say that in the weak nuclear force responsible for the beta decay, it doesn't conserve the parity. The parity conservation means the laws of physics should remain unchanged during the mirror reflection. This is parity conservation. But Shane Wong, a Chinese-American scientist, conducted an experiment to test the conservation of parity, and he found that the parity is not conserved. The parity is not conserved. Wu ने क्या use किया? He uses the sample of cobalt 60 that decays into the nickel 60. Through the beta decay, the sample was placed first in the magnetic field to align the nuclear spin, and it was conducted at low temperature to reduce the thermal effects. And there was also beta detectors around the sample to measure the emitted beta particles. But the beta particles were emitted asymmetrically, means more particles were emitted in one direction than the another. This asymmetry will indicate that the parity is not conserved in weak nuclear force. That's why the weak nuclear force does not conserve the parity. Clear? Means it distinguishes between the left and right-handed particles. Then that contributes to the development of the standard model. So this is very, very important experiment that is known as the Wu experiment. So very important experiment in your nuclear physics, and most of the students do not have any knowledge about this experiment. But this experiment is very, very important. So this is the Wu experiment. The Wu experiment, the beta decay of the cobalt 60 into the nickel 60. The Wu experiment was a groundbreaking experiment in the nuclear physics which challenges the fundamental principles. That is, the parity violation in weak interaction was demonstrated by the Wu experiment. In the Wu experiment, a Chinese scientist takes the cobalt 60 that decays into the nickel 60 through the beta decay, and the experiment shows us that the parity is violated in the beta decay. That means there is no conservation of parity during the beta decay. So first understand what is parity. Parity hai kya? You very well know that the parity means the inversion of the coordinates. Parity means the inversion of the coordinates from a left-handed to a right-handed, or to right-handed to a left-handed. Actually, if the parity is conserved, there should be the equivalence of the left-handed and the right-handed coordinate system. And this is what we think, that the universe do not distinguish between the left-handed and the right-handed. But the Wu experiment, the beta decay of the cobalt 60 into the nickel 60 was a groundbreaking experiment which challenges the fundamental principle of the nuclear physics. The Wu, with his teammates, a Chinese scientist, demonstrated that the parity is getting violated. What is happening to this year? Just wait for 1 minute. अरे सब कुछ उड़ गया भाई. आपने नोट कर लिया था? हैव यू नोटेड डाउन? कर लिया था सबने नोट? चलो फिर दोबारा बताते हैं आपको. देखो, बहुत इंपॉर्टेंट एक्सपेरिमेंट है, किसी ने भी छोड़ना नहीं है ये एक्सपेरिमेंट. आपके मास्टर कैडर के सिलेबस में स्पेशली मेंशन है ये एक्सपेरिमेंट, तो कोई बात नहीं, मैं आपके लिए रिपीट कर सकती हूँ. दैट इज द Wu experiment. That is the, it's U. That is the Wu experiment. parity violation in the weak interaction. This experiment is about the parity violation in weak interaction. Okay, this experiment is about the parity violation in weak interaction. So what is happening is that the 60 cobalt is getting converted into 60 nickel plus emission of electron and plus the emission of anti neutrino. Now in our universe, in our universe, we only found right-handed antineutrino and left-handed neutrino. ओके, व्हाट आर राइट हैंडेड? हाँ जी, अभी ये बताना था आपको कि राइट हैंडेड एंटी न्यूट्रिनो, राइट हैंडेड का क्या मतलब है? राइट हैंडेड का मतलब है व्हेन योर स्पिन वेक्टर एंड द मोमेंटम वेक्टर आर बोथ इन द सेम डायरेक्शन। जब आपके स्पिन और मोमेंटम वेक्टर दोनों सेम डायरेक्शन में होते हैं तब हम उसको राइट हैंडेड बोलते हैं एंड हम बोलते हैं कि इसकी पॉजिटिव हेलिसिटी है। हेलिसिटी क्या होता है? प्रोजेक्शन ऑफ द स्पिन वेक्टर इन द डायरेक्शन ऑफ द मोमेंटम वेक्टर, ठीक है। और एक आपके पास होती है नेगेटिव हेलिसिटी, जब आपका स्पिन वेक्टर एंड द मोमेंटम वेक्टर आर इन द ऑपोजिट डायरेक्शन, दैट इज द लेफ्ट हैंडेड न्यूट्रिनो। तो अब हमने क्या देखा? कोबाल्ट 60 के केस में वी हैव द टू सिनेरियोज, वी हैव द कोबाल्ट 60 के केस में वी हैव द टू सिनेरियोज। द सिनेरियो नंबर 1 इज दैट here is a cobalt 60 in this direction and the electron is getting emitted in the opposite direction of that of the nuclear spin, and its spin vector is in this direction and this is the momentum vector, and that is the left-handed electron. This is the left-handed electrons, and there is a neutrino which has the spin vector and the momentum vector is in the same direction, that is the right-handed anti-neutrino. Okay, and the scenario number 2 is that in which the electron is emitting in the same direction its nuclear spin, that is cobalt 60 की direction जो है उसी में electron is emitted, but there is a anti-neutrino in the left-handed. This is the left-handed anti-neutrino. So there are two scenarios, and both the scenarios are obeying the conservation of linear momentum and angular momentum. There is no violation of angular momentum or linear momentum in both the scenarios, but you should know that positive helicity का मतलब है, या फिर आप बोल लो राइट हैंडेडनेस का मतलब है स्पिन वेक्टर एंड मोमेंटम वेक्टर आर इन सेम डायरेक्शन। एंड हियर इज द वी आर स्टडिंग द, अब हम क्या स्टडी कर रहे हैं यहाँ पे? कोबाल्ट 60 गेट कन्वर्टेड इनटू द निकल 60 प्लस इलेक्ट्रॉन एंड प्लस एंटी न्यूट्रिनो, राइट? नाउ दिस d quark is converting into the u quark plus electron and plus anti neutrino. Beta decay is the only process in which we study the conversion of the quarks, so the Wu experiment was a groundbreaking experiment in the nuclear physics which challenges the fundamental principle of the physics, and it was the experiment which demonstrated that the parity is violated in the beta decay. In this, the Wu with its teammates studies that वो थी एक चाइनीज साइंटिस्ट थी, उसने अपनी टीम में के साथ ये एक्सपेरिमेंट स्टडी किया था 1956 एंड 1957, And the Wu experiments was a groundbreaking experiment in order to explain the challenges, the fundamental concept of the physics. In order to, एक मिनट रुकना, फिर से नेटवर्क प्रॉब्लम आ रही है, स्क्रीन दोबारा ना बंद हो जाए. स्क्रीन दिख रही है सभी को? क्लियर है ना? ये एक्सपेरिमेंट मैं आपको इसलिए करवा रही हूँ बिकॉज इट इज वन ऑफ द मोस्ट इंपॉर्टेंट एक्सपेरिमेंट इन द न्यूक्लियर फिजिक्स. और आपके मास्टर कैडर में इस बार ये स्पेशली एड ऑन किया गया है, तो पूरे चांसेस है कि यहाँ से क्वेश्चन आएगा ही आएगा. सो आज कितनी बारी रिपीट करना पड़ रहा है, कभी स्क्रीन बंद हो रही है, कभी आवाज़ जा रही है. अभी आवाज़ सबको क्लियर आ रही है, सब कुछ सुन रहा है, सब कुछ, कोई दिक्कत? स्क्रीन भी क्लियर है, सब कुछ क्लियर है ना? हाँ, तो चलो फिर से शुरू करते हैं. कोई बात नहीं, आपको समझ आना चाहिए, मैं आपके लिए रिपीट कर सकती हूँ बार बार. So parity means the inversion of the coordinate system from a left-handed to a right-handed coordinate system. So today we are discussing about the Wu experiment. The groundbreaking experiment which challenges the fundamental concept of the nuclear physics. That is the parity violation in the weak interaction. The Wu with her teammates studies the beta decay of the cobalt-60 into the nickel-60, and the Wu find out that the parity is violated in the weak interaction. How does it happen? Now we know that in beta decay, the D quark converted into the U quark, that is neutron is converting into the proton. So what does Wu do? Wu take the very low temperature in order to neglect the thermal effects, and he applies the magnetic field to arrange the nucleus spin in a one particular direction. Now we have two scenarios in which the beta decay process can occur. The scenario number one is that the electron that is emitted is in the opposite direction of that of nuclear spin, and the antineutrino is the right-handed in the one scenario. And in the second scenario, the electron is in the same direction as that of the nuclear spin, and there is a left-handed antineutrino. But both the scenarios follow the conservation laws of energy and linear momentum. From the point of view of conservation law, both the scenarios are possible equally. But what we find out? We find out that both the scenarios are not equally observed in nature. The electrons are emitted asymmetrically. We find out the scenario number one, in which the electron is emitting in the opposite direction of that of the nuclear spin, is more preferable. The universe is more preferable towards the one direction of electron as compared to its another. That is, we always and mostly we observe that the electrons are emitted in the opposite direction of the cobalt-60 nuclear spin, and we observe only the right-handed antineutrinos in the universe. In the universe, we always observe the right-handed antineutrinos and the left-handed neutrinos till now. And the scenario number one is more preferable. There is a asymmetrically emission of the electrons in the opposite of the cobalt-60 nuclear spin. And what does it mean? It means there is the non-equivalence of the left-handed and the right-handed system. That is the consequence of this experiment, that we find out that the parity is getting violated in the weak interaction. During the weak interaction, during the beta decay, the quark changing from D to U, and there is only one preferable direction in which the electron is emitted, and that is the opposite direction. There is no 50-50 probability. There is no equivalence between the two-handedness system, but we find out that there is more priority given to a one scenario rather than the another, even though both the scenarios were allowed by the conservation laws. But even then, because of the parity violation, there is electron always emitted in the one preferred direction as compared to another. There is only one preferred direction as compared to the another direction. What does it mean? It means in weak interaction, in beta decays, the parity is getting violated. And we find out only the right-handed antineutrinos and only the left-handed neutrinos. Clear? And that means the mirror image is not the superposition of its image. And as a consequence of the Wu experiment, a groundbreaking experiment which explains the parity violation in the beta decay, we find out that the In the beta detectors, we use beta detectors, we use the magnetic field, we use the low temperature in order to neglect the thermal effects, in order to perform the experiment in a better way. And as a result of it, we find out that the universe is not symmetric with respect to the parity. There is no equivalence between the two coordinate system. The left-handed coordinate system and the right-handed coordinate system is non-equivalent in the cobalt 60 decay. Clear all of you? So this was the beta decay of the cobalt 60, which is the fundamental experiment that explains the parity violation in the beta decay. Because you can see here in the scenario number 1, the electron are emitted in the opposite direction of the cobalt 60, and there is a right-handed antineutrinos. And what do you mean by right-handed and left-handed? The right-handed, you have two types of handedness, the right-handed system and the left-handed system. One term is the helicity, the positive helicity and the negative helicity. So first of all, what is helicity? Helicity is the projection of the spin vector upon the angular momentum, upon the momentum vector. Helicity and handedness are the very important concept in the particle physics. Helicity is the projection of the spin vector onto its momentum vector. If the spin and the momentum are in the same direction, we call them in right-handed and it has the positive helicity. But if the spin and the momentum vector are in the opposite direction, we call to be have negative helicity. The particle is having negative helicity if the spin and the momentum vector are in the opposite direction. And in universe, we have only left-handed neutrinos and only right-handed antineutrinos. Because in the antineutrinos, we have the spin vector always pointing into the direction of its momentum vector. That is, they having the positive helicity. But in the case of neutrinos, the spin vector is in the opposite direction to that of the momentum vector. And this is the consequence of the parity violation of the beta decay. In weak interaction, there is no conservation of parity. The non-equivalence of two coordinate system in the beta decay explains that the parity is not conserved during the beta decay. Right? Clear? समझ आया सबको एक्सपेरिमेंट? अच्छे से समझ आया? किसी को कोई दिक्कत? अब helicity is a pseudo scalar quantity. The scalars are those which do not change their sign under the parity transformation. But the pseudoscalar changed their sign under the parity transformation, under the inversion, under the improper rotations. Similar like the pseudo-vectors. Pseudo-vectors are the quantities which behave like the vectors under the proper rotation, but they flip their sign. There is additional sign flip during the inversion or reflection. Everyone is clear? Everyone is clear with the concept of वो experiment, or should I explain it again to you? देखो, आज मैं एक्सपेरिमेंट करा रही हूँ, मैं चाहती हूँ कि हर बच्चे को अच्छे से समझ आए. मैं एक नहीं, दो नहीं, तीन नहीं, चार, जितनी मर्जी बार समझ लो, लेकिन ये एक्सपेरिमेंट समझ लो. एक्चुअली व्हाट हैपन इज दैट, मैंने कुछ बच्चों से बात की, मैंने कुछ बच्चों से पूछा, लेकिन कुछ बच्चों ने वो एक्सपेरिमेंट को कभी सुना ही नहीं, कभी समझा ही नहीं. जबकि दिस इज द वन ऑफ द मोस्ट फैसिनेटिंग, मोस्ट important experiment of nuclear physics. And where are you guys? You are learning physics but you don't know about the WO experiment. So today I am not discussing MCQs with you. Today I want to discuss the WO experiment with you. So this was my main aim, to make you understand about the WO experiment. If till now you are not able to understand, I can explain it you again. Yes, जो देख रहे हैं, should I explain the वो experiment again to you or is it okay? आपको अच्छे से समझ आ गया? Should I explain it again? Please respond to me in the comment section. Yes, everyone. पहले भी पैनल बंद हो गया था, मुझे लगा कुछ बच्चों ने नोट नहीं किया होगा. मैंने दोबारा से सारा एक्सपेरिमेंट लिखा, मैंने दोबारा से सारा एक्सपेरिमेंट बताया. कितनी बारी बताया? मैं दोबारा बता सकती हूँ, लेकिन आपको समझ आना चाहिए. जो भी व्यूअर्स देख रहे हैं, प्लीज डू कमेंट in the comment section. Should I repeat it? There is no problem in repeating. I can repeat it, but you should tell me, are you okay with it? रिस्पॉन्स नहीं आने का मतलब क्या है? रिपीट करूं? बोलो, रिपीट करूं एक्सपेरिमेंट को? देखो कोई दिक्कत नहीं है, आपको समझ आना चाहिए। चलो कोई बात नहीं, मैं इसको दोबारा एक्सप्लेन करती हूँ। देखो इतना अच्छा एक्सपेरिमेंट है ना, नाम मतलब नाम से ही आपको होना चाहिए कि हाँ हमने वो एक्सपेरिमेंट पढ़ा है, हमें पता है कि पैरिटी क्यों क्यों वॉयलेट होती है बीटा डिके में। ठीक है, पैरिटी क्यों वॉयलेट होती है बीटा डिके में, हमें पता होना चाहिए। ठीक है, सबसे पहले पैरिटी क्या होती है ये भी हमें पता होना चाहिए। So the Wu experiment is one of the most groundbreaking experiment in the nuclear physics, which challenges the fundamental concepts of the nuclear physics. The Wu, a Chinese scientist, with his teammates, take the beta decay of cobalt 60, studies the beta decay of cobalt 60, converting into the nickel 60 with the emission of electron and antineutrino. Now we very well know that universe have the equivalence of the right-handed and the left-handed coordinate system. But let us study the parity violation in the beta decay through the Wu experiment, and that is the Wu experiment. Cobalt 60 getting converted into the nickel 60, emission of electron, emission of antineutrino. Two scenarios possible. Both scenarios are in accordance with the conservation of linear momentum and energy, but why the one scenario is more preferred than the another? And this is the consequence of this experiment, that is because of the parity violation. There is only the observation of the right-handed antineutrino and the left-handed neutrino in the universe. अब समझ आया? अच्छा, कई बच्चों को अभी लेफ्ट हैंडेड राइट हैंडेड नहीं पता है, मैं इनको बताती हूँ। देखो राइट हैंडेड एंटी न्यूट्रिनो मिलते हैं, मतलब एंटी न्यूट्रिनो की जो स्पिन वेक्टर है इज इन द सेम डायरेक्शन एज दैट ऑफ मोमेंटम वेक्टर. Momentum vector and spin vector are both in the same direction in the right handed and they have the positive helicity. Helicity का मतलब क्या होता है? Projection of the spin vector onto its momentum vector and that is known as the helicity. Helicity का मतलब क्या है? Spin vector and momentum vector are in the same direction. Positive helicity का मतलब है spin vector and momentum vector are in the same direction. अब तो क्लियर हो गया होगा, मैंने पूरा 3-4 बार आपको एक्सप्लेन कर दिया है सब कुछ. अब किसी को डाउट है प्लीज पूछो, डाउट मन में नहीं रखना है. जिन बच्चों ने कभी एक्सपेरिमेंट नहीं पढ़ा था उनको समझ लगा. आई कैन प्रेफर यू द क्रेन बुक, आप क्रेन बुक से गो थ्रू कर सकते हैं. वो एक्सपेरिमेंट में उन्होंने लो टेम्परेचर का यूज किया टू अलाइन द कोबाल्ट 60 न्यूक्लियर स्पिन. सेकेंड, उन्होंने मैग्नेटिक फील्ड अप्लाई किया, ठीक है, for the alignment of the nuclear spin and to minimize the thermal effects. तो आपने लो टेम्परेचर में मैग्नेटिक फील्ड का यूज किया. देन आपने बीटा डिटेक्टर्स को यूज किया इन ऑर्डर टू स्टडी द स्पिन ऑफ इलेक्ट्रॉन्स एंड द कोबाल्ट. तो ये सब हमने किया. पता लगा, सभी को पता लगा. एमसीक्यूज ना डिस्कस करके ये एक्सपेरिमेंट डिस्कस करना बहुत ज़रूरी था, क्योंकि बड़ा दुख हुआ जान के कि कुछ बच्चों ने इस एक्सपेरिमेंट को कभी अपनी लाइफ में पढ़ा ही नहीं है, लेकिन उन्होंने फिजिक्स ऑप्ट की हुई है. सिलेबस में स्पेशली मेंशन है एक्सपेरिमेंट. यहाँ इस एक्सपेरिमेंट को मैंने जितनी डिटेल में एक्सप्लेन किया है, इसके बाहर से क्वेश्चन नहीं आएगा, ये गारंटेड है, ये लिखवा लो. क्वेश्चन यहीं से आएगा, इसके बाहर से क्वेश्चन नहीं आएगा. फिर भी किसी बच्चे को कोई डाउट अभी तक पूछो. है डाउट? किसी को भी थोड़ा सा डाउट हो, किसी भी क्वेश्चन में डाउट हो, कुछ समझ ना आया हो, हैंडेडनेस ना समझ आई हो, हेलिसिटी ना समझ आई हो. अच्छा, एक पॉइंट और होता है कि मासलेस पार्टिकल की हेलिसिटी is equal to its chirality. What is chirality? In which you can't superimpose the image to its mirror image. जिसमें आप superimpose नहीं कर सकते इमेज को mirror image के साथ, उसको आप क्या बोलते हो? Chirality बोलते हो. So in the massless particle your helicity is equal to its chirality. And you should know that helicity is a pseudo scalar quantity. Helicity is a pseudo scalar quantity. Helicity is a pseudo scalar quantity. हाँ जी, देख लो अच्छे से, देख लो, पीछे स्लाइड कर लो, देख लो, कुछ समझ ना आया वो एक्सपेरिमेंट में, आज के बाद डिस्कस नहीं करूंगी कभी, ठीक है? एवरीवन इज क्लियर? चलो, अगर सबको समझ आ गया, सबको क्लियर है, तो क्लास को फिर एंड करते हैं, ठीक है? एनी डाउट यू कैन आस्क मी इन द कमेंट सेक्शन. हेलो, हाँ जी.